integration by substitution. The only thing we really know how to, so now we know how to integrate, if you think about it, we know how to integrate x to the n dx. What do you take the derivative of to get that? That's what I'm asking. This is asking, what do you take the derivative of to get x to the n? Well, whenever you take the derivative of x to a power, the power always goes down 1. Well, that's the power that went down 1. I took the derivative of something and I got x to the n. So what I'm taking the derivative of must be, part of it must be x to the n minus 1. Well, if you have x to the n plus 1, I meant to say. If you have x to the n plus 1, and you take the derivative, you'll get n plus 1 times x to the n. But we don't want that. We just want x to the n. Well, if I divide the right side by n plus 1, that's why this is no longer here, I must divide the other side by n plus 1. And remember, if you have a constant times a function, when you take the derivative, the constant doesn't really come into play. Now, remember, 1 over k is a constant, and when I multiply it by f of x, well, the derivative should be 1 over k f prime. But that's f prime of x over k. That is, this is f of x. This here is f of x over k. And if you wanted to take the derivative of this, it's fine to leave the constant where it is and take the derivative of the top. Okay, that is, when I take the derivative of this, the n plus 1 stays in the bottom, and the derivative of x to the n is n plus 1, x to the n. And we rigged it for the n plus 1's to cancel. So that's the answer. Okay, plus a constant. Because no matter what the constant is, you take the derivative of x to the if you take the derivative of this, well, the derivative of the first part is x to the n plus the derivative of c is 0. So we are getting back x to the n. We are getting this back. So whenever you integrate, you add on a constant. Now, let's just play with that a little bit. First, let's talk about it in words. We'll do a couple of numerical examples, and we'll be done with this part. This is equal to this, plus c. If the power is n, when you integrate, the new power becomes 1 more, and you divide by that same number. The integral of x to the 7 dx. That number 7, 1 more on top, the same thing on the bottom, plus c. Done. The integral of x to the 17 dx. You make this 1 more in the top and in the bottom. Don't forget plus c. If you were asked to integrate. So now, suppose you have some fraction and you want to add 1 to it. Well, a over b is a over b plus, now 1 I'm going to think of as b over b. So I get a plus b over b. Well, if you have this number and you want to add 1, well, what do? Well, the bottom's the same, and the top is the sum of the top and the bottom. The numerator is the top plus the bottom. So if you have a number like 7 over 3 and you want to add 1, the top number will be the sum, 10, and the bottom number stays the same. And to convince you this is right, 7/3 plus 1, I'll write 1 is 3/3. In addition, the denominators are both the same. Keep it, add the tops. I'm getting the same answer. I'm getting the same answer. If you want to add 1 to a fraction, add the top and the bottom, put that in the top, and keep the bottom. So, if you want to find the integral of x to the 1/3 dx, well, it's very simple. To add 1 to the power, you add the 1 and the 3. You add the top and the bottom, and that goes on the top, and the bottom doesn't change. It's still 3. And then you divide by 4/3. Look how I divide by 4/3. 4 over 3 plus c. If you have x to the negative 2/3 dx, the integral of that, well, you add negative 2 and 3. That gives you 1. Divided by the bottom, which is 3. And then you divide by 1 over 3 plus c. And of course, you don't have to divide by 1. 3x to the 1/3. Okay, let's do at least one more. What if x is very negative? Negative so that if I add 1, it's still negative. Suppose you were to do x to the negative 6 dx. Well, the routine. You add 1 to that number, you get negative 5, and then you divide by negative 5 plus c. And let's clean this up. It's understood to be positive on top. Positive divided by negative is negative. The 5, it can stay where it is. And x to the negative 5, since it has a negative exponent, it crosses the division line. Since it's in the numerator, we put it in the denominator with the positive exponent, positive 5. And there's always a 1 on top. Somewhere you can be multiplying by 1. The 1 stays. Plus c. Okay, if you were asked to do the integral of x to the negative 5 over 2 dx, well, part of it is routine. You add 1 to the power. That is, you add the top and the bottom. And you get negative 3. That goes in the numerator of the exponent. And then over the bottom, which is 2. Then you divide by negative 3 over 2 plus c. 2 over negative 3 becomes negative 2 over 3. 3 to the negative 3 halves, since the exponent's negative, it crosses the division line. Since it's in the top, it goes in the bottom. The power is now positive 3 halves plus c. Okay. So we know how to integrate, for right now, just one thing, x to the n dx. But I can change the letters. If the integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c, if instead of x, I put u, then I'll get u to the n plus 1 over n plus 1 plus c. And this is the form we want to write our integrals in when we're doing u substitution. Notice that u is being raised to a power. Okay. So if you have x squared plus 4x to the 5th power times 2x plus 4 dx. We would like to write this in the form u to the n du. Usually, you let u be what's being raised to a power. Here's the power, so that's u. If we let u equal x squared plus 4x, then what will du equal? Well, for right now, you're probably more comfortable in answering du dx. Du dx is 2x plus 4. Now, just like any fraction, if you have 8 over 4 equals 2, 4 times 2 equals 8. Always. This times that equals the top. See, I only want to know what the top equals. I only want to know what du equals, because that's part of my formula, du. So we're going to get in the habit of never putting du in the bottom, and get in the habit of never putting du in the bottom, but rather, I meant to say dx. We're not going to put dx in the bottom, we're going to put it up on the other side. So du is equal to 2x plus 4 dx. du is 2x plus 4 times dx. Okay, well, let's see if we can write this integral in this form. Well, if this is u, then this will be u to the fifth. If u is just x squared plus 4, then it's u. It is what it is. And the power, the exponent, is 5. And this part, looking at my substitution, it says right here, that's du. Okay, du. Oh, now it's in the form of this. Now it's in this form. U to a power, du. That's piece of cake. That's u to the 1 more divided by that number, plus c. But now we have to substitute backwards. After all, if somebody asks you what this integral is, and you tell them, and of course that integral is in terms of x, if you tell them u to the 6 over 6, they're going to be like, what is this person talking about? It's u to the 6 over 6 plus c. Don't randomly guess what u is. You wrote it down. You wrote it down. Don't try to remember. You wrote it down. It's x squared plus 4x. So that's the final answer. We want to write the integral in the form u to the n du. Suppose you had the integral of x cubed plus 2 times to the second power times 3x squared dx. Generally, it's good to let u be what's being raised to a power. Well then du, remember du is like the derivative. The derivative of this is 3x squared dx. Okay, so whenever I see this, I can say dx, and whenever I see that, I can say u. Well, this is u squared, and understood times that, which is du. That's a piece of cake. That's u, make that number 1 more, over 3, plus a constant. And it's u cubed over 3 plus c, where u equals x cubed plus 2. Done. Now, suppose you were given this one instead. Now, you would like something to be u, and what's left over to be du. Well, if I call that u, then that's du. using the same substitution I did up here. Let u equal x cubed plus 2. Now you need to be clever enough to realize that it is u to the n du. U to a number du. It's u to the 1. So then when you integrate, it becomes u squared over 2 plus c. So it's u, that's u, squared over 2 plus a constant. So sometimes it won't have an exponent. Or though there really was an exponent on the x cubed plus 2, it was x cubed plus 2 to the 1. Suppose you have this. I'm going to integrate that. Now, keep in mind that this is x squared plus 1 to the half. In fact, let's do it without the 2. So we have this. So like I've been saying, generally you call what's being raised to a power u. And that's going to be x squared plus 1. So, let u equal x squared plus 1. Well then du, well that's the derivative of this, which is 2x times dx. Okay. So, what I have so far, this is u to the half in the denominator. And I have x squared dx. Well, here's x squared dx, but there's a 2 in front. So divide by 2. Du over 2 is x dx. Okay, du over 2. The numerator, x dx, is du over 2. But in the first video, we talked about how constants can be brought out in the front. And that 2 is in the bottom. It's really half. But this is not in the form of u to the n du. It's in the form of du over u to u to the n. What I can do is I'll bring the u to the power into the numerator as u to the negative 1/2 du. But now, routine again. U to a power du, you add 1 to the power. When you add the top and the bottom, you get 1 divided by 2. Now, in this case, maybe I'll divide by 2. You have 1/2 divided by 1/2. That's going to cancel. Plus c. So the answer is u to the half. That is the square root of u plus c. And u was x squared plus 1. And there's your answer. If you were to take the derivative of this, regardless of what the constant is, if you take the derivative of this, you're supposed to get x over the square root of x squared plus 1. Why is this going to work with no matter, regardless of the constant we put here? Because the derivative of the constant is a constant. It's 0. The derivative of a constant is 0. Okay, so sometimes the u to the n, you have to move from the denominator to the numerator. So suppose you have 5x times the cube root of 1 minus x squared dx. I think it should be a habit that you bring the constant in front. X times the cube root of 1 minus x squared dx. So it's 1 minus x squared to the 1/3. That means 1/3 power, cube root. 4th root, quarter power, dx. Generally, you let u equal what's being raised to a power. What's being raised to the 1/3 power? 1 minus x squared. So then du will be, well, the derivative is negative 2x dx. That'll be du. Alright. And you can write this in any order. You should at least think this. It's 1 minus x squared to the 3rd times x dx. Well, this piece is u, so this whole piece is u to the 3rd. So you got 5 integral u to the 3rd. Probably a cleaner way of doing it than I did last time is I have x dx. Here it is. I just need negative 2. Now this only works with numbers, not with letters. I can multiply inside by negative 2. Do that in red because we inserted it. I'm going to multiply inside by negative 2, but then I have to come outside with my negative 2 in the denominator. As I multiply inside by negative 2, I divide outside by negative 2. And outside will be negative 5 over 2. Like I said before, that piece is u to the 3rd. And now, negative 2x dx, that is du. So it's negative 5/3 times this. But this is in the form of u to the n du. So I add 1 to the power. That is, I add the top and the bottom, and I get 4. I add the 1 and the 3, I get 4. And I divide by 3. And then I divide by 4 over 3. Coincidentally, the 3's cancel. And I get negative 5 u to the 4/3 power over 4, in both cases, plus c. And u is, no guessing, it's 1 minus x squared. And that would be your final answer. You have x squared over 1 plus 2x cubed to the 8th power dx. So you let u equal 1 plus 2x cubed. Then du will be 6x squared times dx. Well, this is u to the 8 in the denominator. In anticipation is u to the negative 8 in the numerator. So what's left over? What did I not talk about? X squared dx. I didn't talk about that. Well, I need a 6. X squared dx, if I multiply it by 6, then I can call it du. So I'm going to multiply it by 6, and then I'm going to divide by 6. And now I'm going to say this piece, the numerator, is du, and the denominator again is u to the 8 in the denominator. So it's u to the negative 8 in the numerator, which is what I already put. Okay, now this integral is supposed to be routine. You add 1 to the exponent, and then you divide by that same number. Okay. 6 times 9 is 54, but the numerator is positive, and the denominator is negative, so the final answer is negative. And the numerator is u to the negative 9, plus c. But we're not supposed to get negative exponents. So I put the u in the bottom as u to the 9. So I put the 54 in the bottom. The u to the negative 9 I put in the bottom. The negative side I put in the top. Where did the 1 come from? You can, since there's nothing left in the numerator other than a sign, you can multiply by 1. That's where the 1 is. If there's nothing left, it's always understood to be 1. Suppose you have that. That's a 2. I'll let u be what's raised to a power. Now, you can argue that t is being raised to a power, but the derivative of t will not be 1 plus 1 over t all squared. If it's going to work, it's going to work the other way. That is, by letting u be 1 plus 1 over t, not just t. Okay, well then, remember that 1 over t is t to the negative 1. So then du will equal, the derivative of 1 is 0, plus the derivative of 1 over t is the same as the derivative of that. Plus minus is minus. Bring down the power, make the new power 1 less. That's the derivative, dt. For du, you have to put the dt on the other side. But this is the same as negative 1 dt over t squared. Okay. So this portion is reserved for u to the power, u squared. I'm hoping that up to a multiple, that's du. If only I multiplied by negative 1. Multiply inside by negative 1, multiply outside by negative 1. After all, they multiply out to 1. Usually, if you put 7 inside the integral, you have to put out 1/7. Because when you multiply 1/7 by 7, it's 1. Well, the only time you put in the same number and bring out the same number is when you're plugging in negative 1, or when you multiply an inside by 1. But why you would multiply inside by 1, I'm not clear why you would do that. In fact, you don't get anything by doing that. Okay, so what's going on here? We have the minus 1 in front. That part is u squared. All of this, especially with the minus 1, that's du. But this integral is very doable. It's negative u to the 3 over 3 plus c. It's negative u to the 3 over 3. And u is 1 plus 1 over t. There's your answer. Sometimes you may have to be very clever, more clever, to make your substitution. For example, if you have 9 minus y times the square root of y d1. Now, there's two things that you can call u. That's somewhat immediate. You can let u be 9 minus y. So let's write that. Or you can let u be the square root of y. That is y to the half. Now, if you let u equal 9 minus y, then du will equal, well, the derivative of 9 minus y is negative 1 dy. Now, if you make the substitution, let's see what happens. Oh, so let's see. We talked about what that part is, 9 minus y. Well, that's u. So this equation means, multiplying both sides by negative 1, that dy is negative du. So this part is done. It is negative du. But what about the square root of y? Well, you can do that, but then you're going to get into a jam, I suspect. If you bring this over to the left side, it'll be positive, and you bring that over, because you want y alone. So y will equal to 9 minus u. So square root of y is square root of 9 minus u. Square root of 9 minus u. So what we have here is u integral of 9 minus u times negative du. The negative you can bring out in front if you prefer. The question is, did this help us? Is it in the form of u to the n du or anything else? See, if you can distribute, say, the u, if you have the n, so let's do this integral to motivate what I'm saying. Well, okay, let's just finish up this. So letting u equal 9 minus y didn't seem to help us very much. So I claim. Now let's look to see what happens if u equal the square root of y. So then du will equal the derivative of this. You bring down the power, then you make the new power of y 1 less. That'll make the power negative a half, which will make it positive a half in the bottom, times du. The thing, well, something's wrong there, times dy. Times dy. Let's see what this does for us. 9 minus y, well, if I square both sides, I'll learn that u squared is y. So 9 minus y, u squared, times the square root of y. The square root of y is u, times dy. So this tells me that dy is 2y to the half du, which is 2. And remember, square root of y is u du, times dy, which is 2u du. Like I said, I like to bring factors that are just constants in front. So now we have 9 minus u squared times u, which is u squared, times du, and the 2 I brought in front. The thing we benefited by letting u equal the square root of y is there are no square root signs here. That is, I can now distribute. If you distribute, you just get a nice polynomial in u. It's a nice polynomial in u. Here's my 2. The integral of 9u squared, you make the 9 stays there, it's a constant. Remember the integral of a constant times f of u, or f of x dx. The constant can come in front. U cubed over 3 minus the integral of that. U to the 5 over 5. And of course this becomes 3. let's clean this up a little bit. So, if I get a common denominator of 5, so I already have 1 5, what I'll have left here, 3u cubed, I have to multiply by 5 on top and 5 on the bottom. So I get 15u cubed, the 5 on the bottom I factored out, minus u to the 5th, plus c. And at the very, very top I will put the answer. So it equals to 2/5 times 15 u to the 3 minus u to the 5th. For u is the square root of y. It says so. U is y to the half. So if I cube that, I get y to the 3/2. I multiply the 1/2 power by 3. Minus what? Minus u to the 5th. The u is square root of y to the half, to the 5th power will become minus y to the 5/2. And minus some silly error, there's the answer to that one. That one was completely different. Although one can argue that I did let u equal what was being raised to a power. Let's try one more like that. That'll probably do it for this section. If you were given this problem, this is not to be done by any kind of substitution. Just distribute. Okay, 8x to the 3/2 minus x to the 5/2 dx. Oh, we need to redo the last one. I don't know what I was thinking. So now, whether you write this out or not, you should be thinking this. It's the first integral of f of x, minus the integral of g of x. Whether you write that or not, you should rethink it. You should even say, oh, the constant comes out in front. So you get 8. This integral is, well, you add 1 to the power, get 5/2. Then you divide by 5 over 2. Minus, you add 1 to the exponent by adding 5 and 2 and dividing that by 2. 5 and 2 is 7. And then you divide by 7 over 2 plus c. And just cleaning this up, this should just be 16. Okay, now the last problem. I don't know what I was thinking. You do it exact one. If you have 9 minus y times the square root of y dy, and so square root of y is y to a power. You just distribute. Sorry that I blew that. You distribute. You get 9y to the half minus a half plus the understood 1 becomes 3/2 dy, excuse me, dy. Now integrating these should be routine. First you integrate the first one, and the 9 comes in front. Integral of y to the half Well, you add 1, and then you divide by 3 over 2, minus. You add 1 to the power, and then you divide by 5 over 2, plus c. And 3 goes into 9 3 times, so it's 6. Y to the 3 halves minus 2y to the 5 halves over 5 plus c. Okay. I'll do the problem that I thought we had. When you just had y to a power, you were able to distribute. You were able to distribute, but what if you have this? What if you have y minus 2 times y dy? I didn't need those last parentheses, those last set of brackets. Now, you cannot distribute because of the square root sign. I would then call what's underneath the square root sign u. Let u equal y minus 2. I would let u equal what's underneath the square root sign. Because if you just had the square root of u and you were multiplying by polynomials in u, you can then distribute. Because this is really u to the half. You can distribute. So I'm going to let u be y minus 2. Let u equal y minus 2. Well, then du equals, the derivative of this is 1 times dy. Okay, and so this will become, this piece becomes the square root of u. dy becomes du. Now here's what I mean when I say you have to be honest. You now have to say, well, what's y? You have to justify every piece. Well, if you add 2 to both sides, you get that y is u plus 2. Okay? U plus 2. And like I've been saying, now you can distribute. You get u to the half times u plus 2 du. When you distribute, you get u to the 3 halves plus u to the 1 half. Integral of all of that du. Now this becomes u to the 5 over 2 divided by 5 over 2 plus u to the 2, u to the 3 halves divided by 3 over 2 plus c. So you get 2/5 u, which is y minus 2 to the 5 halves power plus 4/3 times u to the 3 halves plus c, where u is y minus 2. Okay, calling this part, because we can't distribute across it, calling this part u is a good move to make. Okay, that finishes the section on integration by substitution.